All right, let's talk about the secret language that decides whether your favorite app is amazingly fast or painfully slow. Today, we're decoding code efficiency. Have you ever just stared at your phone, wondering why one app is blazing fast and another one feels like it's wading through mud? You hit search on one thing and bam, results. On another, you could go make a coffee and come back. It's a super frustrating but universal experience. And the reason for it, well, it's not magic, it's a choice. And the answer, it turns out, is all about choosing the smartest path. That's it. It's a design decision that happens way before an app ever gets to you, and it makes all the difference in the world. So let's get right into it. Section 1, choosing the smartest path. We're going to look at how programmers actually think about these kinds of problems. To really get this, let's use a great analogy. Imagine you're planning a road trip, say from Kumasi to Accra. You pull up your map, and what do you see? A bunch of different routes, right? Some are shorter, some have less traffic. As the driver, you have to pick the best one, the most optimum route, probably the one that saves you the most time. Well, that's exactly how programming works. Those routes you can take, in software, we call them algorithms. It's just a fancy word for a step-by-step recipe to solve a problem. And just like that driver picking a route, a programmer has to look at all the possible algorithms and choose the most efficient one for the job. Okay, but that leads to a really big question, right? How do you even measure which path is the best? I mean, you can't just run every option on every computer in the world and grab a stopwatch. The time it takes on a supercomputer is going to be way different than on a 10-year-old laptop. We need a universal yardstick. And that brings us to our next big idea, measuring an algorithm's growth. Because here's the secret. Efficiency isn't really about raw speed in seconds. It's all about how well an algorithm scales. So what's a growth rate? It's basically how much slower an algorithm gets as the job gets bigger. Think about it. Sorting a list of 10 names is easy. Any method is going to be fast. But sorting 10 million names? Whoa, now we have a problem. That's where a bad, inefficient algorithm just completely falls apart. Here's a brilliant analogy to help this click. Imagine you go to a shop. You buy some delicious wake, and you also grab a bottle of water. When you get back and someone asks what you bought, you just say, I got some wake. You don't even mention the water. Why? Because the cost of the wake is the big deal. The water is so cheap in comparison, it's basically a rounding error. The wake is the dominant cost. Believe it or not, programmers do the exact same thing, but with math. They might get a crazy-looking formula for an algorithm's runtime, something like n to the fourth plus 2n squared plus 100n plus 500. They look at all those parts and they do the Wakian water thing. They find the term that grows the fastest, in this case n to the fourth. The rest is just water. They simplify the whole thing down and focus only on that dominant term, because when the input n gets huge, that's the only part that really matters. And to talk about this stuff, to classify these dominant terms, programmers have a special shorthand. It's a secret language, really. And that brings us to our next section, the secret language of Big O. This is all about giving an algorithm a grade for its worst-case performance. So what on earth is Big O notation? Simply put, it's a way to describe the absolute worst-case scenario. It's the upper limit. It answers one critical question. As my data gets bigger and bigger, what's the absolute worst this thing is going to perform? It's all about being a professional pessimist, planning for the worst possible day. This graph shows it perfectly. See that wiggly line? That's the actual, messy, real-world runtime of some code. Now look at that smoother curve above it. That's the Big O. Notice how after a certain point, the Big O line is always above the real runtime? It acts like a ceiling. It's a guarantee that says, hey, no matter how messy it gets, your performance will never be worse than this. And using this, we can basically give algorithms a grade, like a report card. This table shows some of the most common ones. Up top, you've got O of 1, constant time. That's the holy grail. It's amazing. Then you've got O of log n and O of n, still really good. But as you move down the list to things like O of n squared or, oh boy, O of 2 to the n, the performance gets bad, and it gets bad fast. We're talking terrifyingly slow. Now, just so you know, Big O isn't the whole story. There's also omega for the best case and theta for the average case. But honestly, you're going to hear programmers talk about Big O 99% of the time. And the reason is simple. When you're building a system that millions of people rely on, you can't just hope for the best day. You have to plan, design, and build for the absolute worst day. Okay, that was a lot of theory. But what does it all mean in practice? Let's bring it all home in our final section, Why Efficiency Changes Everything. Let's look at the real-world payoff. Let's look at a classic example, finding something in a list. The first route is a linear search. You just check every single item, one by one from the start. Its grade, O of n. The other route is binary search. This one is way smarter. It jumps to the middle of a sorted list and throws away half of it with every single check. Its grade, O of log n. And let me tell you, that is a phenomenally better grade. And you can see the difference right here. With a tiny list of just 16 items, in the worst case, our simple linear search takes, let's say, 16 milliseconds. But our smart binary search? It only needs 4 milliseconds. Even on this tiny scale, you can see a clear winner. And I know what you're thinking. Okay, 16 versus 4, not life-changing. But this is where the whole idea of growth rates becomes mind-blowing. What happens when it's not 16 items? What if it's a million? Or a billion? Suddenly, that gap isn't small anymore. It's astronomical. We could be talking about the difference between a search that takes a fraction of a second versus one that could literally take days to finish. And that right there brings us full circle. This is the answer to our original question. This is why one photo app can search through billions of your images in an instant, while another struggles just to find a name and a few thousand contacts. It's almost never about the computer's power. It's about the power of choosing a better algorithm, a smarter path. So this secret language of efficiency, this way of thinking about how things scale, it's not some abstract concept. It is the engine running underneath almost every single piece of our digital world. The question is, as data gets bigger and problems get harder, what will this secret language build next?